Hello, I'm going to be talking about some work that we at Cambridge have done together with Cranfield and Rolls-Royce, looking at the separation on the external surfaces of aircraft engine nacelles in specific off-design scenarios. The work is really motivated by the fact that in order to reduce the environmental impact of aviation, it's necessary to use engines with larger bypass ratios, and as a result, larger diameter fans. Now, if we were simply to take an existing engine design and scale it up, the nacelles would be proportionally bigger and have a larger wetted area, which would increase the drag, counteracting the benefits of the higher bypass ratio. It's therefore necessary to design nacelles which are much slimmer, and these must therefore have more severe surface curvature around the nacelle lip, which can be problematic in certain scenarios such as diversion windmilling. Diversion windmilling refers to when the engine shuts down during the cruise phase of flight, and as a result features quite a high Mach number but a low angle of attack. When the engine shuts down, there's a lower mass flow rate through the engine, and so the stagnation point moves inside the nacelle lip, and the flow then accelerates around this highly curved nacelle lip and becomes supersonic. The supersonic region terminates in a normal shock, and if this shock wave is strong enough, it can separate the boundary layer that's developing on the external fan cowl surface. And the drag associated with this separation can have a big impact on the overall aircraft performance. But we still aren't able to predict this complex flow phenomenon particularly well. And that's partially because we don't quite understand the flow physics involved, but also because the computational methods typically used in industry aren't able to reliably predict the onset or the scale of separation. So the aim of this study is to try and replicate the key flow physics from this complex three-dimensional problem in a quasi-two-dimensional fundamental wind tunnel study. In order to do this, we make use of a blowdown transonic wind tunnel, where the flow comes in from a settling chamber and contraction, through a test section and out through the diffuser. So in order to determine what we put in the test section to replicate diversion windmilling, we start off with 3D computations of a full-scale nacelle under diversion windmilling. And we look at what the 2D flow field in a plane that we extract from these 3D computations looks like. In particular, we consider two streamlines, one internal to the engine and one external to the nacelle, and these then form the basis of the geometry of our wind tunnel rig. Now, inside the wind tunnel geometry, the nacelle model itself is based on an optimized nacelle geometry. You might notice that it's inverted for easier interface with the existing tunnel structure. But this then means that the top wall corresponds to a streamline internal to the engine, whereas the bottom wall, the orange line, corresponds to an external streamline. Now, the bottom wall has actually been adjusted slightly to account for boundary layer effects and the differences between a 2D and a 3D flow field. And in particular, this inverse design makes use of RANS computations of the wind tunnel flow path in order to replicate the Mach number distribution on the external fan cowl surface between the 3D full-scale nacelle and the wind tunnel rig. Now, a key parameter determining the behaviour of diversion windmilling flow fields is the position of the stagnation point, which in a real nacelle is determined by the mass flow rate through the engine. This is replicated in our wind tunnel rig by installing bumps of different heights on the top wall, which affect the flow through the upper channel. As the bump gets bigger, the mass flow rate through the upper channel is reduced, and as a result the stagnation streamline moves and the stagnation point moves further downstream inside the nacelle, as we would expect. So now that we've got our design for our wind tunnel rig, we need to make sure that it replicates the key flow physics from diversion windmilling to ensure that the data from the rig improves our physical understanding and is able to improve computational methods of this flow field. In order to check that this is the case, we need to verify that the flow field is both qualitatively and quantitatively, as we might expect. To do so, we perform tests with 3 different bump heights, and these, according to RANS computations using existing methods of the wind tunnel flow path, should correspond to different flow behaviour on the purple external fan cowl surface. The smallest bump in blue corresponds to an attached flow, whereas the intermediate case corresponds to incipient separation, and the largest yellow bump corresponds to well-developed separation on the external fan cowl surface. So qualitatively, we'd expect the flow field to contain a supersonic region with a terminating normal shock, and to progress from an attached flow field to a fully separated flow field between the 3 bumps that we test. Quantitatively, we want to know whether we can use this data in order to validate and improve computational methods. So using these tests, we want to know to what extent experimental data matches preliminary RANS computations that use existing methods. To start off with the qualitative flow behaviour, we use Schlieren imaging to highlight the key flow features, where we can see there is indeed a supersonic region which terminates in a normal shock. And we can also visualise the boundary layer downstream of this shock wave. Now, as we move to bumps of greater heights, we can see that not only does the shock wave move further downstream, but it also becomes more prominent. We can see that we go from a smeared shock foot to a bifurcated lambda shock, which is characteristic of flow separation. And we can also see that as a result, the boundary layer downstream becomes significantly thicker. To understand why this is happening, we can start off by considering the isentropic Mach number distribution on the inside of the nacelle lip around the stagnation point. Now, for the smallest bump case, the stagnation point lies somewhere between these two lines, where the isentropic Mach number is 0. And as we increase the bump height, we can see that this stagnation point moves further downstream inside the nacelle lip. The movement of this stagnation point then has an impact on the pressure distribution on the external nacelle surface, which we visualise using pressure-sensitive paint. Indeed, here we can see we've got quite a two-dimensional flow field. We can also see the supersonic region and the terminating normal shock. And as we move to larger bump heights, where the stagnation point has moved inside the nacelle, the size of the supersonic region has increased and the shock has moved downstream. Now, we can quantify this by considering the profile on the centerline of the tunnel, where we can then see that as well as moving downstream, the shock wave has also increased in strength. This stronger, more downstream shock wave also has an impact on the surface flow topology that we can visualize using oil flow. When we mark on regions of corner and central separation, we can see that we go from the mainly attached flow for the blue bump through to well-developed separation across the entire tunnel span for the largest yellow bump. Now, this difference in separation has an impact on the boundary layer downstream of the shock wave, where for the smallest bump, we can see that we've got a very thin boundary layer. It's only 0.8 millimeters thick, whereas as the size of separation increases, the boundary layer at this point starts to become thicker and eventually ends up more than 2 millimeters thick. So now, by doing these tests, as well as verifying that the flow field is indeed qualitatively as we would expect, we've also started to get an idea of the key mechanisms at play. From a quantitative perspective, we want to compare our experimental data to existing RANS computations, and one way we can do this is by considering the pressure profile on the external fan cowl surface, in particular zooming in on the region around the shockwave boundary layer interaction. This comparison firstly shows us that the prediction is pretty good overall, and in particular, the shockwave position and the shockwave Mach number are both captured pretty accurately. The one key difference between the two is that the RANS computations has a more smeared shockwave than the experimental data, but this is a known limitation of RANS. Now, looking at the boundary layer profile downstream of the shockwave, we can see that for the smallest bump, the attached flow field case, everything is pretty well predicted, even the velocity profile within the boundary layer. However, as the shockwave becomes strong enough to separate the boundary layer, we start to see that the velocity profile inside the boundary layer becomes incorrect. And then for the largest bump height, even the free stream velocity and the boundary layer thickness aren't predicted accurately. And again, this is another limitation of RANS, which is well known. So, qualitatively, we've seen that we do indeed have this supersonic region terminating in a normal shock. And we've started to get an idea of the mechanisms at play that link the movement of the stagnation point inside the lip to a thicker boundary layer downstream of the shock boundary layer interaction. And quantitatively, we've seen that even the RANS predictions of using existing RANS methods are able to mostly predict the flow field. The key differences being the smearing of the shock wave and the deviation in boundary layer profile as the shock wave begins to separate the boundary layer. But these are both known limitations of RANS, which this set of experiments is planning to tackle. And so, by performing these preliminary tests on the wind tunnel rig, we now have increased confidence that the wind tunnel rig does indeed capture the key flow physics from a diversion windmilling scenario, and so can be used to improve physical understanding and computational methods to predict external fan cowl separation. Thank you very much for your time.